allow me, I'm going to kind of refine the title a little bit and make it a little more specific. What I'm going to talk about is how to make a Lisp. So how many people in the audience are familiar with the programming language Lisp or have used it? Okay, a reasonably high number of hands. Cool. Okay, that's actually probably more than I would have thought. Marvelous. Well, for those of you who aren't familiar with Lisp, I'm going to go in some detail discussing what Lisp is, where it came from, what makes a language a Lisp. To refine the title further, I'm going to talk about how you'd make a Lisp as Gaeilge. So I'm an Irish language speaker, and I'm going to talk about how I built an Irish programming language, a programming language that uses the Irish language for its keywords. And of course, given the location, to refine that further again, I'm going to talk about how you'd build a Lisp as Gaeilge in Python. So I think as far as reflecting what I'm actually doing, that's probably the most accurate title, but I realise that it does contain the name of two programming languages, and it's written in two different natural languages, so it's not the best title as far as clarity is concerned. But this is kind of what I'm driving for today. So by means of introducing myself, my name is Neal Riain. I'm a former astrophysicist by training. I did my PhD in astrophysics just down the road here in Trinity, left the field about 2 years ago, and since then I've been over in London. I'm working there as a data scientist at Amazon, so doing kind of machine learning, AI data things there. So this is kind of a long way outside my wheelhouse, but as I said, I'm an Irish language speaker, and what I did was I decided to build a programming language that makes use of the Irish language. So I don't know how many Irish speakers we've got in the house tonight. I guess not that many, but this is the Irish word for calculator. This is Áireamhán, and this is the name of the language that I put together. So there don't exist a huge number of programming languages in languages other than English. It's kind of the primary language for programming, I guess, as we're all pretty much aware, despite the fact that lots of languages, I would hazard the majority of languages are developed by people who speak English as a second language. Python, of course, was developed in the Netherlands by Guido van Rossum. Ruby, very popular language, developed in Japan. Lua was developed in Brazil. So we've kind of settled on English being the language that we use to do this in, but for keywords and the rest. But it's not necessarily the main language of people who develop the languages. There do exist a small number of languages in the major European languages. So let's say French and German, but they're mostly from the 70s and 80s, and I think primarily uses teaching tools. There's a version, I believe, someone can correct me on this if I'm wrong, but there's a version of the C language called C, as in Spanish for yes, it's in Spanish, and it's used as a teaching tool there. But there don't exist any programming languages in minority European languages, like Irish, for instance. So I decided to right that wrong and go about putting together Áireamhán. So with all that throat clearing done, I'm going to give you an outline of what I'm going to speak about for the next little while. So I'm going to introduce what a Lisp is to begin with, and why Lisps the way they are. I'm going to talk about the history of Lisp and show you some of the syntax, why it looks the way it does, and kind of give you an idea of what the language can do. I'm then going to show you a little bit of Python, this being Pycon. I'm going to talk you through how you would go about implementing, how you'd go about implementing a Lisp in Python, which is pretty much what I did. And then I'll wrap up by showing you guys some Áireamhán, because I think it'll be quite neat to show you guys what I've actually put together. So let's jump right into it and talk about what is a Lisp and why is a Lisp the way that it is. Well, you've been noticing maybe that up to this point I've been saying a Lisp rather than a Lisp, because Lisp is not a single language, it's in fact a whole family of programming languages. The most prevalent would probably be Common Lisp, the aptly named Common Lisp, and MIT Scheme, which go back quite a long way and are both very commonly used Lisp languages. But Lisp has lots of other successors. There's a version written in Python that I've actually come across called Hy, H-Y, which is a kind of Python interoperable Lisp. There's a lot of Clojure, for instance, and an awful lot of the functional programming languages we've got now are in some sense successors to Lisp. They're kind of carrying on the project that it began. But more than just being a family of languages, I would say that Lisp constitutes a paradigm for programming. Lisp is a way of thinking about computation and a way of thinking about implementing programs. It's, perhaps to go further than that again, it's maybe one of only two really principled and holistically executed paradigms for programming that we've got, the other being the C paradigm, I would say. And as computers become more powerful, and as the thing we're optimizing for more and more is the programmer's time rather than the optimality of the code, I think we're moving further away from the C paradigm, the kind of memory management pointer paradigm that C implements, to something that looks an awful lot more like the Lisp paradigm, something that's more functional, something that's much more high level, and I think Python is probably evidence of that, something that provides the user with an awful lot more abstraction and an awful lot more kind of freedom and functionality. So to give you a little bit of background of the Lisp programming language, I'll start with this guy here. So this angry Santa here is John McCarthy. So John McCarthy, I think, has reasonable claim to call himself the father of AI. He invented the phrase artificial intelligence, and he ran the AI lab at MIT for decades. And he's a pioneering figure in that field, so someone I'm familiar with from my own work in that kind of neck of the woods. But he also, in the late 1950s, developed the language Lisp to do AI research, what we would probably call now good old-fashioned AI, the stuff that came before deep learning, also known as the stuff that didn't really work. He developed that language to try to implement some of the things that he was trying to do. Some things that actually kind of look like chatbots now, like question-answer machines, that kind of thing. So this is him writing some Lisp, I guess, on this machine back in the 1960s. One connection that I came across in preparing this talk, one thing that I found quite interesting, is that I guess with a name like John McCarthy, you could guess that he's got some kind of Irish lineage, but John McCarthy's father was actually born in the West Kerry Gaeltacht, which is quite a nice connection between Lisp and the Irish language there. I think John maybe would approve of what I put together. Though maybe not, he seems like quite a prickly fella. So to give you an idea of the world that Lisp was born into, in the late 1950s, computer programming looked a little bit like this. This is an 8-hole punch card. Now maybe that's not completely fair. It probably looked a little more like this, but it's not a total lie because this is backwardly compatible directly to those punch cards that were around not very long before. And this is Fortran. I'm sure many of you are familiar with and have very strong feelings about Fortran. Probably not very many of you have very strong positive feelings about it. But it was the language. It and COBOL were the two primary languages in the 1950s, and it was the language for scientific computation. And this program here, I think, is written in Fortran 2. It's actually quite hard to find examples of Fortran from back that far, but I think this was the version that was around when Lisp was created. And it's a program to solve a quadratic equation, as you can see. Maybe you can recognize some of the stuff in there. The equation we all had to memorize for the junior cert, minus b plus or minus whatever the rest of it is, it's implemented here in this piece of code. And some of it looks pretty familiar to you, to us, I would think, as programmers. You can see, he's defining variables, doing basic mathematical operations. Fortran is formula translation, so it's kind of translating a formula into machine code. It also contains some things that look less normal, like it's got lots of these numbers in the sidebar, and the if statements look weird. If disk, do 15, 25, 35, I guess perform those operations in that order. So it's got lots of things that I guess we'd recognize and some things that seem a little bit unusual. But this is the world that Lisp came into. And Lisp was, I think, a revolution at the time, a thing that changed an awful lot around how programming languages were considered. And it introduced some things that we still have to this day. It introduced conditionals as we would understand them. So you'll notice that Fortran, which I showed you there, did have conditional statements in it. It had that if statement there, but it doesn't have an if-then-else construct as we would really recognize it. This was introduced in the Lisp language. It also provided for recursion. So recursion is a pretty fundamental thing in computation, and the capacity for a function to call itself from inside of itself. You have a function called foo, which somewhere in foo calls foo. You could do that, I guess, in Fortran back then, but it would just go back into the same function again with the same variables and undo all the work you'd just done. So it wasn't a particularly useful thing, and it didn't become available in the language until the 70s. It also provided first-class functions. So functions, as you would think about functions as a mathematician, rather than just as ways of packaging code, functions are things that can take in functions as input, they can return functions as output. This came directly from McCarthy's paper in 1957 defining the Lisp language. It gave us other things right from the get-go, stuff like garbage collection, which is now, I think, common to the vast majority of high-level languages. Lisp, by its nature, produced an awful lot of intermediate objects as you did a computation, produced an awful lot of variables that you didn't really want to hang around. So McCarthy introduced an automatic way of going around and freeing up memory that wasn't being used anymore. It also introduced the REPL, the read, evaluate, print loop, the kind of human-in-the-loop computation that I guess we're all very familiar with as Python programmers. So the read, evaluate, print loop being it reads in a statement, you write in a console that reads in a statement, evaluates it, prints the result to the screen, and loops back around waiting for the next statement. So the IPython console, or the Jupyter notebook that I'm giving this talk in, being an example of a REPL on steroids. That came directly from Lisp. So you had all these amazing kind of developments from the language, and I guess the sensible thing to do now is to maybe show you what the language looks like. And it looks a little bit like this. I think the one thing that people would know about Lisp, even if they'd never used it, is that Lisp has lots and lots of parentheses in it. There's an XKCD about it, and if there's an XKCD about it, then you can bank on the thing being pretty true. So Lisp does have a lot of parentheses in it, and I'll show you later. Áireamhán also has a lot of parentheses in it. As a result, it's a fully parenthesized language. But there's reason behind it, and I think I'll try to introduce why. So what I'm going to do is I'm going to talk you through some of John McCarthy's 1957 paper, which introduced the Lisp language. In this paper, he defined some kind of primitives for computation, or almost axioms for computation. And I'll introduce them now one by one and just show you what they do, and hopefully give you an idea of why they do what they do. So some of them will seem quite familiar as a Python programmer. Some of these things are pretty much directly as they appear in the Python language, appear in Lisp. Some things will seem a little bit less so. So let's begin with some basic definitions. I think we can safely enough agree on this one. It's a sensible enough thing. The empty list evaluates to none, to nil. It's an empty thing. There's nothing in it, right? So an empty list is not simply an empty list. Once you evaluate it, it's nothing. Fair, I think. We'll also give ourselves true, a Boolean true, and we'll give ourselves a Boolean false as well. McCarthy doesn't even give himself a Boolean false. He just says that Neal is false. So even here, this is syntactic sugar that I'm introducing beyond what he had back in 1957. But let's start off with these three things, and let's define some functions. I'm giving the Irish translation of the functions as well to remind you all that why we're here is to talk about the Irish language. That's what we're all in it for today, and at the end we're going to go through the Tishel Ginnaduk. So let's begin with probably the most alien thing, I think, to a lot of people who would come to Lisp. This is not something that you'd see, for instance, in Python, is the quote statement. So quote in Irish is ahrital. And the quote statement, first of all, you'll notice the parentheses. Everything is wrapped in parentheses in Lisp. And when you quote, for instance, the empty list, it does not evaluate the empty list. You don't get nil back. What you get back is the empty list, right? It just returns to you the thing you gave it, exactly as it is with no evaluation. You could, for instance, quote something that is not a valid Lisp expression, and it would just give it back to you. So it's a way, in some sense, of introducing data into the language right off the bat. You can quote parentheses 1, 2, 3, 4, 5. It's not a valid Lisp expression, but the quote statement will just return it to you as you gave it to it. It seems unusual, but I think you'll see in a minute why it's a sensible thing to have. The next thing that he defines is atom, or in Irish, adav, and I'm sticking with the MIT scheme syntactic convention of keeping question marks at the end of things that return booleans. You'll see that as I go through. Again, it's wrapped in parentheses, and atom evaluates whether or not something is an atomic object. An atomic object is like a number, for instance, a symbol. The empty list is atomic because it evaluates to nil, but any list that is not empty is not atomic, right? I think that's, again, fair enough, seems intuitive, right? If a thing has more than one thing in it, it's not an atom anymore. So that's the definition that McCarthy gives for this function. The next one we define is the equality function, or corhamla in Irish. Again, we wrap it in parentheses, and you'll notice another weird thing that we do here, and that is that we use prefix notation. So Lisp enforces throughout prefix notation. Every Lisp statement has the structure operator followed by operands, followed by arguments. So in many languages where we would say left equals right, here we say equality, these two objects. And in this case, an empty list is indeed equal to an empty list. So it evaluates this statement to true. Reasonable? I think so. Now, maybe a slightly more unusual thing, a very common operation in Lisp, but not something that's that common outside of it, is the char operator, or count in Irish. So the char operator takes in a list as input and returns the first thing. It's not a very intuitive name. I think it's short for something like content addressable register or something totally non-intuitive like that. But it just returns the first thing in a list, for instance. So here we can quote 1, 2, 3. So we enter this kind of list object. Char gives you back the 1. Fair enough. CDR, tone in Irish. Again, terribly named, and terribly named in Irish too. CDR is the opposite of char. It gives you back everything that the char doesn't give you back. So if char gives you back the head of the list, CDR gives you back the tail of the list, gives you back everything else, right? So the list 2, 3 in this case. To continue with that, we've got const. So const is just const because some things you don't mess with when you're translating the entire Irish language. Const is, I think, a very common thing to many functional programmers. Consting is a verb that people would use. You would const an object onto a list, which means you prepend it onto the list. The opposite of Python's append operation, let's say. You take a thing, you put it at the head of a list. Okay? The if statement, that's that McCarthy introduced in his paper. It's the first time that this has been introduced, and it's an if statement as we'd recognize it today. If some condition is the case, do the first thing, otherwise do the second thing. An if then else statement. Okay? a very I would say succinct notation for an if-then-else statement. If condition, do this. If not, do the second thing. And finally, the lambda. So lambda just translates to lambda, and we're all very familiar with lambdas, I think, anonymous functions in Python. All functions in Lisp are defined by use of lambdas. And lambda looks like this. It's lambda, arguments, expression, and then an environment. And an environment is just the list of values that the arguments correspond to. So you can have a lambda, x, y, z, some expression which is made up of x, y, z statements, and then you'll hand in afterwards an environment which are just the values that x, y, z will take when you're evaluating this function. Fair enough? So I guess you're all thinking now at this point, so what, who cares? That seems like quite a long-winded thing to do, to give you 7 examples of 7 unusual primitives, some of which seem natural, some of which seem a little bit random, like why would you bother defining something like CDR in a language? So the amazing thing about what this is here, and I know you can't read this, and I know this maybe means nothing to people, but this is a pretty staggering thing. This is page 13 of the Lisp manual, and this is 2 functions, apply and eval, which have been often called the kind of Maxwell's equations of computing. These are the most succinct and wonderfully put together thing once I explain to you what exactly they're doing. But this is a full Lisp interpreter written in the Lisp language, using just those 7 primitives that I've introduced. So using only the 7 functions that I've talked about there, you can write an interpreter in the Lisp language using just the 7 primitives, as I said, that will walk through any Lisp expression, evaluate it, and return its output. And this is the really big thing that Lisp brought about. It gave us all those wonderful things I listed up to this point, but it also gave us, it was the first language to be self-hosted, which is the first language that was able to compile itself and run its own code. And McCarthy did it like this. So to give you an idea of why that is, I think, a fairly staggering achievement, at that point, Fortran, which as I said was the major other language, had taken about 20 man-years of work to implement. What McCarthy did was define 7 axiomatic functions, the 7 functions I just showed you, implemented those in machine code, and using just these 2 functions here, wrote an entire interpreter for a language. So I think that's a pretty cool thing. It's a deep thing. It's a thing I think about a lot. A thing that troubles me a little bit, but it's amazing. It's a staggering achievement. So using, as I said, just 7 functions, a couple of helper functions that he defined a little bit earlier here. These 2 functions here give you the whole kit and caboodle, an entire functioning programming language. Now, okay, it's not a very useful programming language right at the moment. It doesn't have any numbers in it, for instance. You don't need them really. You can just use like an empty list that contains 2 empty lists in a list is the number 2, 3 empty lists in a list is the number 3, whatever. You don't need numbers really, but you can define those things fairly easily on top of this and give yourself something that's very functional, right? Something that you actually use. So the nice thing about this is that if you can implement these 2 functions effectively and a little bit of other stuff on top in any programming language, what you developed is a Lisp interpreter. So if you can put together these 2 functions in Python, for instance, why not Python? Look where we are. Then you've got yourself a fully functioning Lisp interpreter. And that's pretty much what I did. So to get to the Python part of the talk now, I'll show you a little bit of how you might go about doing this in the Python programming language to build your own programming language. So a hat tip to these 4 somewhat unusual looking white guys before I go any further. They're all, I like to think, a little bit weird looking in their own way. They are from top left to bottom right. They're Stephen Russell, Peter Norvig, Paul Graham, and Michael Nielsen. And these guys have all written incredibly interesting blog posts, code, books about Lisp, all of which are available in the Jupyter notebook that I'm presenting here. It's on my GitHub. If anyone wants to delve a little bit deeper into this stuff, you can go to my GitHub, get the notebook. There are some citations in there, and the code will all run later on, you'll see. To give you an idea of who they are, so Steve Russell was actually John McCarthy's PhD student at MIT in the 1950s. He's the guy who actually had to sit down and write the code after John came up with this wonderful idea. So he's the man who actually put together the Lisp interpreter. He's also the man who invented the world's first video game. He's credited as the first video game developer, which is really cool. Peter Norvig, who's carefully camouflaged beside him there, is the head of engineering at Google, or like some amazing job title like that. Chief Imagineer at Google or something. He's the guy behind the whole thing. And he wrote an amazing series of blog posts and a lot of code on Lisp. He's a big Lisp guy. The bottom left is the man behind Y Combinator. It's Paul Graham. So Paul Graham and Hacker News and all the rest. And he wrote a couple, I think, of really excellent books on Lisp and something that's really worth looking up. And Michael Nielsen has also written a lot on it too. So if you want to delve a little bit deeper into the stuff I'm introducing, a hat tip to those 4 men is I think something I'm required to do at this point. So let's jump right into some Python code, because that's where we are, and that's what we're going to do. So let's say we start off with a Lisp expression, like that line that I've given there. That's an example that I gave before. Car, quote, 1, 2, 3. It should evaluate to the number 1, right? We're quoting the list 1, 2, 3. We're taking the first thing out of it. So, well, the first thing you need to do if you want to write a programming language is you need to be able to break a sentence like that down into tokens, okay? And you can do that mercifully in Lisp using regular expressions. One of the nice things about Lisp is that it's got a very, very simple syntax. Everything's wrapped in parentheses. Everything is itself, in some sense, a list, right? Both the data, 1, 2, 3 is in a list, but also the whole thing is in a list, so everything's a list. So it's very, very regular syntax. So you can parse it using a simple regular expression. That's not a very simple regular expression. It took me quite a long time to write it, but it is a regular expression that will parse any arbitrary Lisp expression, right? That's, to start with, quite a staggering thing, to be able to put together a full language that has such a simple and regular syntax. It's something you can't do, for instance, in Python. Python's got quite an irregular syntax, in fact, white space and all the rest. So you need something an awful lot more powerful. Generally, you do it using what's called the EBNF, the Extended Backus-Naur form, which is a much more powerful formalism for, to be technical about it, it's like 2 steps further up the Chomsky hierarchy. A regular expression is the simplest possible thing. So this is literally the simplest possible programming language with the simplest possible syntax. So just using that regular expression in this loop, you can, for instance, tokenize this expression I've given you. Break out the parentheses, the functions, the functions and the inputs one by one, right? And you can see that example there. Again, all this code is in the notebook. If you want to go online and download it, you can play around with it. It all runs. Once you've done that, you want to build something called a parse tree. So that's the next step in building a programming language. You take in your raw string, you break it into tokens, you turn those tokens into a tree-like structure that you can then navigate and evaluate the layers of the tree as you go along, right? A nested structure, a hierarchical thing. This function here will do that. As I said, just at the bottom there, you'll see tree is equal to parse tokenize this thing. So the tokenize function that I wrote just before breaks it out into a series of individual characters. The parse function that you see right there, it's got recursion in it. So recursion is a necessary thing. It was necessary for John McCarthy's project that functions be first class and that recursion be right there at the top of the language. In fact, the first word of the paper that he wrote about Lisp is recursion. So you walk through it and you build this parse tree, which is just a nested list structure. Again, you'll note again at this point that the regular syntax saves us, the very, very simple syntax of Lisp, that parse tree that I got at the bottom, that nested list structure, is almost exactly the same as the string I put in, right? All I've done pretty much is replace the parentheses with square brackets to make it into a Python nested list structure, right? Hell, I could have made a list of tuples out of it if I wanted to, just by directly evaluating it. So regular syntax saves us again, and we get a very, very simple parse tree. So you can imagine this as a structure that's, I mean, it's linear here, but you can imagine it as a nested thing with at the bottom the leaves of the tree being atomic objects, being things like numbers or symbols, right? Basic, unbreakable things. And then at each layer above that, we're collecting together those atomic objects, performing functional operations on them, all the way up the tree till we get to the top, perform the last operation, and hand back the evaluation, right? So let's do that. Let's walk through that evaluation tree from bottom to top. You can do it very simply here. I've only defined 2 functions. If you want a fully functioning Lisp, you'll need at least the 7 that McCarthy gave us. But there you go. That's a fully functioning Lisp interpreter. The regular expression breaks down the string token by token. The parse tree is built by that simple little function that I showed you before, and this one here just checks if it's a car, do this, if it's a quote, do that, and there you go. You can evaluate that simple expression. As I said, if you want to evaluate any arbitrary expression, you'll need to go a little further. You'll need to define exactly 5 more things into this evaluation function, but that will be it, and that's what I did for Áireamhán. So to remind you all again, the reason that we're here is to talk about the Irish language, and how I built an Irish programming language is simply by implementing this in Python with Irish keywords. And using that, you can walk any arbitrary Lisp expression, evaluate it, and return a result. So we're at this point of the talk where I get to show you guys some of the language. So I'm going to do some live typing, which terrifies me. Tell me at what point you can actually see this. Is that getting near to big enough? Yeah. That's big enough now? Yeah? Okay, cool. Great. So I guess I'll begin with Python, because again it's Pycon, and the sensible thing to do is to begin where we can all agree. So let's define a very IPython REPL. The REPL is something that Lisp gave us, so right away we're in comfortable Lisp-y territory. And let's define the simplest possible recursive function, I would say, or probably the most famous recursive function. I think it is literally the first one that McCarthy defines in his paper. It's the factorial function, right? So let's say define a factorial function, something that takes in a number n, right? If n is equal to 1, return n. Otherwise, return the product of n and the factorial of n minus 1, right? So we can all agree on that as a definition for factorials. We don't need any refreshers on what factorials are. It's just the product of all the numbers up to some value n, and that can be easily recursively defined as the product of n and all the numbers up to n minus 1, and we just keep going down. Once we get to 1, give back 1. That's a simple factorial function, right? We can call that on the number 10, for instance, and I presume that is the factorial of the number 10. I'm not going to calculate that by hand, and I've got no reason to second guess Python on this. That seems like a reasonable answer to me. So let's do the same thing over here. Tell me when it's big enough. Big enough now? Visible to everyone? Cool. So let's use Áireamhán to do the same thing, just to give you an idea of what the language looks like. So you call it in the same way from bash, and you get a REPL. It says hello, and it waits for some input, right? So let's do the very same function. Let's just define a factorial in Irish. So Sonic is the Irish for define. Sonic is the Irish for define. So define factorial, right? What is factorial? Well, it's a function, so it's a lambda. All functions are lambdas in Lisp and in Áireamhán. It's a lambda which takes in one thing, takes in the number n, right? If that n is equal to 1, mata, if n is equal to 1, you'll note at this point the prefix notation that's common to all Lisps. The equality operator goes first. If n is equal to 1, then give me back n. Otherwise, give me back the product of n and the factorial of n minus 1. Let's cross our fingers and hope that works. Close off a bunch of parentheses. That's not quite enough. That's a number of parentheses I need to close at the end of that expression. There's method to the madness. There's a reason for parentheses to be there. Okay, so that looks, I think, quite like the Python expression that we had before. Reasonably so, I would hope. I'm really hoping this works. Factorial of 10. It's the same number, I believe. Yeah, great. Okay. That's, I mean, somewhat of a surprise to begin with because I implemented this code. But that's, I think, very similar to the Python code that we had before. We define an object. That object is a function. It's a lambda. It takes one input. If the input's this, do this. Otherwise, do that, using that very condensed if-else syntax that McCarthy introduced, right? Pretty good. So one thing that I guess some of you will know about Python, I presume many of you do, is that Python has an inbuilt recursion limit, which just limits what you can do with things like this. You can't, there's a limit in the machine. You can check what it is on your machine. You can change it if you like. I probably wouldn't recommend it because I don't know enough about how the Python works in the internals, but I guarantee it'll brick your machine. So let's say if I try to compute the factorial of 2000, it waits for a while and then it gives me a recursion error, right? Python won't do that. Python won't let you recur more than, I think on my machine it might be 1,000 times. So you can build 1,000 nested stack frames in each function. You can build another function inside of it. You can do that down to a depth of 1,000 times, at which point Python just hard limits and says, no, you've done that too many times. You're going to break your machine. And that's the end of that story in Python. You simply can't get around it. There are no optimizations that will fix that. And unfortunately, that's something that we inherit over here. If I try and call the same factorial function with the same input in Áireamhán, it dies in a much less graceful way. But give me a break. It dies, okay? So that's the end of that story there. But one nice thing about Áireamhán, and this is entirely related to that very simple syntactically refined kind of syntax that we defined in Lisp, and how easy the parse trees are to build and how easy they are to walk and navigate, is we can, even inside of Python, build a thing that's not available in Python. We can build tail recursive optimization inside Python. So I'm not sure how many of you are familiar with tail recursive optimization. Some of you may have heard it back in like a CS lecture many, many moons ago and barely remember what it is. Some of you may use it every day. I don't know what kind of things you guys do. But tail recursive optimization is a way of rewriting recursive functions so they've got their answer at the tail, effectively. So what that means is, in Python, for instance, or in the code that I just showed you, we come in with a number n, we keep going down till we find an n that's equal to 1, keep building functions inside functions till we get down to an n that's equal to 1, and then we have to come all the way back up that chain again and hand the answer out, right? A tail recursive optimization keeps, let's say, a counter or an accumulator at each step of that nested recursion, keeps the answer or a guess at the answer with it all the way down. So when it gets to the end of the recursion, it doesn't have to come all the way back up the tree. It can just hand out the answer at that point, right? That's a tail recursive optimization in a nutshell, ignoring pretty much what a tail recursion optimization is. But here's how you would implement it in this language, for instance. So you Sonic, another thing, which is called fact again. It's still a lambda, because it's still a function, but this time it takes two inputs. It takes n and accumulator. Oh, maybe I'm going over time, but let's stick with this. It takes in two things. It takes in n now and an accumulator, right? If n is equal to 1. Let's do the same thing. This time give back the accumulator. The accumulator is going to hold the answer at each step, right? And otherwise, then call fact again and give it n minus 1, right? Subtract 1 from n, and the product of accumulator and n. So the accumulator increases by the product of n each time, n goes down by 1. The accumulator, you can kind of see how this will store the answer at each step, and we don't have to come back up at the end, we can just give out the accumulator. Cool, right? Close off a whole bunch of parentheses. That was the right amount. Marvelous, that was actually very neat. And let's call that on the number 2000, for instance. And it doesn't work because, well, you get to see an error message in Áireamhán. You got a 5. I was Exula. I was looking for 2 things, and an accumulator. You gave me 1 thing. You gave me 2000. That was silly of you. Don't do that. So I'm going to do that again. Give it 2000 and the number 1. So I'm starting off with the base case is the number 1. The thing you're going to accumulate on is the number 1. And that, I believe, is the factorial of 2000. I would say, I guess. So if you want to compute factorials, I think it's demonstrably the case that Áireamhán is the language to use to do that in. But there's an example of the language of some of the syntax and of some of the things you can do with it. So to go back over here, I'll wrap it up at that point, and I'll leave you go. To mention who I am and where you'll find me, I'm on GitHub at Neal OR. I'm also on Twitter at something similar without the other kind of thing. You can regex the difference. I'm online there. And you can install Áireamhán from the pip repository. So pip3, I'm emphasizing pip3 because it uses FODAs, it uses UTF-8 things everywhere, obviously, because it's Irish. So you won't be able to use Python 2 for it, unfortunately. And if you'd like to fork it and make it better, then do feel free. And I suppose at that point I'll leave you and take any questions that you may have. Thanks a lot. We run for time?
No, we're good. So we've got 5 minutes or 10 minutes for questions. So I don't know if we've got a microphone in this room. So project your voice, I guess.
Any questions?
I have a question.
Yeah.
So how did you get into sort of writing your own programming language? I mean, given your background in astrophysics, I guess you sort of self-taught in a way. Are there any resources that you used or?
Yeah, well, so how I got into it, it just seemed like a fun thing to do. It's something that I've wanted to do for a long time, to build a language, as Gaeilge, as an Irish speaker. I thought it was a fun thing to do. It's a tremendous way to learn how computers work, to learn how an interpreter actually functions, gives you a great idea of what's going on under the hood of a programming language. And as far as resources, I couldn't ask for better than the 4 guys who I mentioned there, as I say, whose citations are in the notebook if anyone cares to do some research on it. You'll find this on my GitHub and you'll find the citations in there. They've all written books, blog posts, code. Peter Norvig actually wrote a Lisp interpreter himself in Python to demonstrate how it's done, and a very simple one to demonstrate how it's done. And if you want to start off with putting a language together, I would recommend it as a hobby. It's one that you'll benefit from. You won't make anything useful out of it, but you'll learn an awful lot about how code works under the hood. So that's where it came from. Anyone else? 101? That's a shame. All right. Well, thanks a lot anyway, guys. Thanks very much for listening.